Hi everybody, in this video I am going to talk about the valence shell electron pair repulsion theory, or VSEPR theory. This theory allows us to predict the geometry of molecules given the number of bonds and the number of electron pairs. Although it is not a perfect theory, it works most of the time, so we will stick to it for now. And this theory is based on the idea that lone pairs repel the electron clouds of atoms, which cause them to shift away. So, as an example, take a look at the one I just circled. Here you can see that this electron pair is actually repelling these two atoms, or more specifically their electron clouds, and because they're repelling, these two atoms want to get as far from that lone pair as possible, so it decides to shift downwards, and that's why the two atoms are not in a straight line, but instead they are pointing away. And if there are no electron pairs, such as here, then the atoms will naturally want to move as far away from each other as possible, because their electron clouds are both negative charges, and like charges will repel. So they'll get as far away from each other as possible, and the farthest they can get away is by going across from each other. So that's how VSEPR works fundamentally. Now let's talk about something called a steric number. A steric number simply tells you the number of atoms and lone pairs that are attached to a central atom. And if you have an unpaired electron, such as an electron that's alone, then you can count it as a lone pair for simplicity purposes if needed. So let's do an example. So over here you see the steric numbers 2 through 6, and as you can see, this atom E is attached to two atoms X, and that's why the steric number is 2. While for here, the central atom E is attached to three things, two atoms and one lone pair, so that's why it has a steric number of 3. So now that we talked about steric numbers, let's talk about some things you need to know about this chart. So what you will do on your own is that you will memorize all these shapes, and I know it might sound like a daunting task, but with enough practice, you can eventually get it. So let me tell you some very important bond angles that you should know. For a linear molecule, the angle between the two bonds is 180, or very close to that. For trigonal planar, the angles between the bonds will be around 120. For tetrahedral, the angles between the bonds will be about 109.5. So don't look at the 109. Think of it as 109.5, because that is the ideal angle. Now, the last thing I want you to know is that for square planar, the angles between the bonds are 90 degrees. So a square planar might look like this, with 4 atoms here, and the angles will be 90 degrees apart, as shown there with that right angle that I just drew. So those are the 4 fundamental angles that you should generally know. Now, let's get to the shapes. I'll go through steric numbers 2 through 4, and for the rest of them, you can either simply look at them and see what they look like. So for this example, you can see that the atoms are arranged in a way that looks like a seesaw if you kind of tilt this over, and then you'll get something that looks like this. It's like two people sitting on a seesaw. So you could either memorize these shapes and how they look like, or you could memorize the shapes and the steric number and the lone pairs that correspond to it. So it's really up to you what you want to memorize and which one best fits you. But I will teach you a way in the future that will save you a lot of time, I think, and it'll also be very helpful. So let's go over steric numbers 2 through 4. Steric number 2. The only thing that could occur here is two atoms being attached, and that will be 180, and it will be called linear. For steric number 3, you can have 3 atoms attached, each 120 degrees apart, and that's called trigonal planar. Or you could have two atoms attached and one lone pair attached, and you would get a bond angle of, it says, less than 120. So maybe something like 118, 117. So when it says less than, it means like maybe 2 or 3 degrees less, and it's not extremely less. It's just like a little bit less, if you know what I mean. So this will be known as bent. Now, for steric number 4, you have tetrahedral, which is where 4 atoms are attached to a central atom. You have trigonal pyramid, which is where there are 3 atoms attached and a lone pair attached. Now, last but not least, we have a bent, which is where we have 2 atoms once again and 2 lone pairs this time. And notice how the bond angle will be much less than 109. So when you see a double less than sign, then you know that it's going to be much less. And much less is like, for example, I drew here water, H2O. The bond angle for water is going to be about 105 degrees. So what I mean by much less, I mean like 4 less, which is not a lot in perspective, but it's still a lot for a molecule since every degree matters when it comes to chemistry. Now, let's take a look at one random structure from steric numbers 5 or 6. Let's take a look at, how about this, square pyramid. So a square pyramid, if you know from geometry, is just a pyramid with a square base, and it kind of looks like that. So as you notice, this looks like a square pyramid because it has 5 corners, or 5 atoms, you can think of it that way. And you see how the angles are around 90 degrees apart. And this is because, if you think about it, over here, you see that there's a square planar, and you know that square planars are 90 degrees apart, as we saw over there. So that makes sense, doesn't it? Now, what about these 2 atoms that point up and down? Well, if you notice, this angle right there is really close to 90 degrees. So therefore, every angle, when it comes to a steric number of 6, tends to be around 90 degrees. And the only exception is the linear model, where the linear model will always be 180. So I can't just keep on talking about this forever. You just have to take a look at these shapes for yourself and practice them on your own. And don't worry, I will go over a few questions with you for you to visualize how this works. Now, before I begin doing examples, let's take a look at a trick that I like to share. So, there's something called electron geometry. The electron geometry is the geometry formed by the electron clouds of the atoms and lone pairs. So, molecular geometry only includes the atoms, but the electronic geometry includes both the electron clouds of the atoms and the lone pairs. So, one electron geometry corresponds to each steric number, and the electron geometry is the same as a molecular geometry with 0 lone pairs. So that means that if you have a steric number of 4, then your electron geometry will be the one with 0 lone pairs, or tetrahedral. So keep a note of that because I will show you how that will work soon. Now, this will be very useful for drawing these shapes, determining the name of the shapes and the bond angles. But of course, just take a look at this chart and, let's do some practice problems, and with the chart, see if you can figure out things. But before we move on, I want to talk about one more thing. So, I wanted to talk about wedges. So, what are wedges? Well, these wedges describe the geometry of these atoms in the 3D world that we live in. So, here's how it works. So in this picture, you can see something called CH3Cl, or chloromethane. So this has a tetrahedral molecular geometry. And notice how I drew a plane there. This is a 2D plane. And for bonds on this 2D plane, I will use regular lines to identify them. So in this example, these 2 hydrogens lie on the plane, so I will draw them as lines. Now, things that are in front of the plane, such as this hydrogen here, will be indicated by a solid wedge for the bond. So for the bond, you will draw a solid wedge, such as the yellow one over there. Now, if the atom is pointing away from the plane, or behind the plane to be more specific, then you will use a dashed wedge, which looks like this, but it can look like this as well. It's your choice whether you want to draw it this way or this way, although this way is the more legit way. So this 3D geometry only is applicable for steric numbers 4 and up, and that is because if you're looking at steric numbers 2 and 3, you notice that they are flat on a plane. So because they are kind of just flat on a plane, you don't need to indicate anything that's in front of the plane or behind the plane, so you don't use any wedges for those. But for steric numbers 4 and up, notice how there are wedges, there are solid wedges, and there are dashed wedges all over the place. So we will look at this when we do the examples, but just keep a keen eye out for these geometries. And one more thing to note, you can draw lone pairs as a bond attached to, a lone pair like that, or you could draw it like this, where you have like a cloud that's around a lone pair, or you could simply just put the atom, like there's an oxygen there, and just put the lone pair like that. It's up to you how you want to draw it, but I prefer this way because, it's the way we did for Lewis structures, so I want to keep consistency. Now, let's actually move to the very first question. We will look at hydrogen peroxide, and notice how peroxide is O2 2-, and this is a polyatomic ion, but this is a covalent molecule, so in this case, we are using a polyatomic ion to describe a covalent molecule, and you won't see this very often, but sometimes it happens. So let's draw H2O2. So you're going to have an O there, an H there, and an O there, and an H there. So everything has the number of bonds that it typically wants, and this will have 2 lone pairs and 2 lone pairs. And I think this will be the Lewis structure. Now let's take a look at the electron geometry trick that I showed you. So we need to first find the steric number. The steric number is the number of lone pairs and atoms attached to the atom we're looking at. So, in this example, the steric number for each of these oxygens is actually 4. So since we know that the steric number is 4, it's going to correspond to a tetrahedral shape. So let's draw this out. So it's going to look like a tetrahedral, and let's put the H on the plane. So we have a plane here, and let's just say that the H is on the plane, and then this will be attached to an O, and let's just say that our lone pairs will be the ones pointing toward and away. So when you draw these things, since it has a steric number of 4 or higher, we have to use solid wedges and dashed wedges. So for these kinds of drawings, we have to choose 2 bonds to be on a plane and 1 bond to be in front and 1 bond to be behind. So I think the bond that I'm going to choose to be in front will be this one, and it will look like this. So if it's in front, you're going to use a solid wedge and put a lone pair there, and this will be the one behind the plane, so it will look like that, and that will be behind. So this is the geometry for the bond for this oxygen here, and notice how this oxygen has a bond that's identical to the other oxygen. So they both essentially have the same electron geometries if you think about it, but they're just kind of just like flipped over. So what type of geometry is this? What type of molecular geometry is this? Well, if you think about this, or if you just, draw the atoms and draw it in a tetrahedral shape, then you might notice that these 2 atoms are in a bent configuration. And in this case, since we have 2 lone pairs, And since this is tetrahedral, we remember that this is going to be around 109.5 degrees. So that's the bond angle for here and here. So they're both around 109.5 degrees. Now, the actual bond angle is going to be 101.9 degrees. Notice how it's significantly less than 109.5, but it's kind of close to 109.5. So if you put 109.5, you should be fine. But if you want to be a bit more accurate, we can reference the angle for water. Remember, water just looks like H2O2, but with an extra O in a way. And remember that water had a bond angle of 105. So, in a way, since the electron geometries and the molecular geometry is the same as for H2O2, then you could be more accurate and say that this is not 109.5, but around 105 degrees. And that's closer to 101.9 degrees, which is the actual angle. And you don't have to know this. This is just from like experimental data, but you are expected to be able to estimate the bond angle. And let's try to get as close as possible. So for this case, we are going to mimic the bond angle for water and say this is, around 105 degrees. Or you could just say 109.5. It's really up to you and whether you want to be more accurate or less accurate. So let's take a look at the actual molecular geometry using a kit that I made. So it's in this picture over here, and as you can see, it's bent like that. And now let's move on to the next question, CO2. So we're going to draw a C in the middle, attach it to two O's, and these two O's will have two lone pairs each. So what is the geometry of this? Well, looking at this, since the atoms want to be as far away from each other as possible, and since it's a steric number of 2, then we know that this must be linear, and linear molecules have a 180-degree angle between the bonds. And this was pretty quick and simple, and the actual geometry looks like that. I know it doesn't really look like 180, but if you think about it, it's very, very close to 180. It just isn't close to 180 because my modeling kit wasn't perfect. So let's move on to the next question. Ammonia, or NH3. So let's draw this without the wedges for now. So NH3 looks like that, and it will have a lone pair there. And let's see, this has a steric number of 4, so this is going to be tetrahedral. And because it has a steric number of 4 or higher, it is going to have some 3D parts to it. And if it has 3D parts, it is going to have wedges. So I like to keep the top and the right on the plane, and I like to make these two the fronts and backs. So let's do that. So I'll make this H the back, so this H will have a squiggly line, and it'll be in the back. Or if I want to be more legit, I would use the dashed lines, and that would be more legit, but it looks a little bit messier, to be honest. And for here, I'll do a solid wedge. So these two are not going to be on the plane, but these two are. Now, I could just put this bond like this, but since it's on the plane, I'll just keep it like that. So since this has a tetrahedral geometry, then it is going to have bond angles of around 109.5 degrees. Now, the actual bond angle is going to be around 107 degrees. And now let's figure out the molecular geometry. So the molecular geometry is going to be trigonal. So I'm going to draw it out. Trigonal pyramid. And I'll show you why this is so soon. So it's trigonal planar because if you look at the image, it looks like that. It looks like a pyramid with a triangle for its base, and the lone pair is sticking up. And as you can see, these two are on the plane, while this one's facing front and this one's facing back. So a 3D representation, such as through a picture, is really helpful in this case. Now, something I want you to know is that for trigonal pyramids, the bond angle is generally going to be around 107 degrees. So this 109.5, yeah, you could totally put that, but for cases such as those like for H2O, where it's going to be 105 for 2 lone pairs and 2 atoms, and for ammonia, which will be 107 for 1 lone pair and 3 atoms. These two numbers are kind of good to remember. So for bent with 2 electron pairs, it will be 105, and for trigonal pyramidal, it will be 107. So these are more accurate numbers in a way, and it's your choice if you want to memorize it or not, but I would. So I would just say that NH3 has 107-degree bond angles, and this will replace 109.5. Or you could just keep 109.5, but it's your choice. So let's move on to another shape, xenon tetrafluoride. So xenon is going to form an extended octet, so I'm going to do that. And let's not forget the electrons. So 1, 2, 3, 4, 5, 6. Gotta do that for all the fluorines. And now that we've done that, let's figure out the electron geometry. Oh, we forgot one thing. Xenon has 8 valence electrons, so we have to do that. And now let's figure out the steric number. The steric number is going to be 6, so it's going to be octahedral. And an octahedron looks kind of like this. So I'm going to draw the bonds out. And it kind of... Oh, that's a terrible drawing. Wait. Actually, no, it didn't turn out that bad. It kind of looks like that. It kind of looks like 2 square pyramids put next to each other. So an octahedral shape will have 90-degree angles throughout. And for this case, I think I want to keep these 4 on the same plane, since if you think about it, you could kind of imagine it like that. And then I will put the 2 fluorines on the front and the back. So this will be the back and this will be the front. So I'm going to change this picture just a little bit, and I'm going to do this. I'm going to put this in the back using a squiggly line or a dashed line, up to you. And I'm going to put a bold line there. And there you go. This is the structure for xenon tetrafluoride with its 3D components. So what is the shape of this? Well, think about what the shape is by looking at the atoms. So the atoms are in a flat surface, as you can see in this picture. These 4 atoms drawn over here are in a flat surface, and they're spread out evenly with a 90-degree angle. And I just gave you the bond angle, and this will be called square planar. And in real life, or using modeling kits, it looks like that. And it's tilted downwards because I can't place the thing straight up because it doesn't balance on here. So it looks like that. So you see how it's flat and it's 90 degrees apart. So that's xenon tetrafluoride. Now let's look at sulfur hexafluoride. So sulfur and 6 fluorines put together. So I'm going to redraw this because I can already see where this is going. So 1, 2, 3, 4, 5, and 6. And this is steric number 6, so it's going to be an octahedral for its electron geometry and for its molecular geometry. So octahedral. And let me check if that's right. Is it octahedral? Yes, it is. There you go. So it's octahedral. And let's see what we want to put in the front and the back. So I think I'm going to put this in the front and this in the back. So this is going to be in the front and this is going to be in the back. So it looks like that. And I forgot to put the lone pairs. Never forget the lone pairs on the fluorines, because that's very important. And it's easy to forget when you're doing these things. So just make sure to double check everything whenever you're drawing these things. And it looks like we're done. So in real life, it looks like that. And look at that, it's a tetrahedral. So I'm going to trace it out for you and show you that it kind of looks like that. So yeah, next question, I3-. So we drew this in the previous video about Lewis structure, so I'll just draw it out for you. So it's like that, like that, like that, an extended octet, of course. And it'll go like that, like that, like that, like that, that, and that. And let's check the geometry for the middle. So for this middle one here, it is going to be a steric number of 5, and that corresponds to trigonal bipyramidal. So it's going to look like this, and it's going to kind of look like that and go down like that. And that looks confusing at first, but once you see the image, it will make sense later. So trigonal bipyramidal. So let's think about this. So the eye is in the middle, and it's attached to two atoms, so I'll try to draw them as far away from each other as possible, because remember, atoms want to be as far away from each other as possible, and that will make the tips. And let's put the things that are on the triangle. So the electron will be over here, and over here. So notice how a trigonal bipyramidal is made up of a trigonal planar and two, I guess, axes that go up and down. So this is going to have 120 degrees, and this is going to be, I'm assuming, 90 degrees. And this is going to be our electron geometry. But now let's take a look at our molecular geometry. Notice how the atoms are as far away from each other as possible. So when we draw this, we want the atoms to be as far away from each other as possible. So in this case, they will be 180 degrees apart, and this will be actually linear. And if you didn't know how to draw this, you could have just easily memorized this from the chart, and voila, you could have figured it out that way. But I like to draw it out to figure it out, so that's what I do. And now let's figure out what we want to put for the front and the back. So I think these two will be my plane, and I will put these two in front and this one in the back. So this one will be the back, and these two will be the front. It makes sense when you look at it, but you know, the answer is going to be linear, and it's going to have invisible electrons that I didn't put, but that's perfectly fine. So let's actually go back and see how it actually looks like so you are reminded of that. So it looks like this. So let me find it. It's like that. So the 3 electrons are on the plane, and the 2 atoms are as far away from each other as possible. So I think I got the angles all right. So let's move on to the next question, which turns out to be PO43-. So phosphate looks like this, and it has a steric number of 4 with no lone pairs, so we can assume that this structure will be tetrahedral since it has 4 bonds and no lone pairs. So this will be tetrahedral, and we know that tetrahedral has 109.5 degrees for its angle measures. Now, let's draw the 3D structures using the bonds. So I think that I'm going to make this my solid wedge and this my dashed wedge. So this is how you draw phosphate, and let's take a look at the actual structure. It looks like that. It looks pretty tetrahedral to me, so let's move on. C3H4. So this is going to be like this, and let's try to figure out the molecular geometries from the steric numbers. So the steric number there is 2, and this is 4, and since there are no lone pairs to worry about, the electron geometry will be the same as the molecular one. So this will be linear, so I'm going to write linear, and it's going to be 180 degrees, around there. And since this is 4, it's going to be tetrahedral, and this is going to be 109.5 degrees. And since this is tetrahedral with a steric number of 4 or higher, let's draw the wedges. So for the dashed wedge, I'm going to put it here, and for the solid wedge, I'm going to do that. So there you go. And in real life, it looks like that. So pretty linear to me, pretty tetrahedral to me. Let's move on to nitrite. So nitrite will look like that, and it has a -1 formal charge here. And now let's figure out the steric number. It's going to be 3 because 1, 2, 3. And this is going to have an electron geometry of trigonal planar, but the molecular geometry is going to be a little bit different. So since there's an electron here, we could draw it like that, of course. This was one of the 3 ways that I taught you how to draw lone pairs. You can choose any of the 3. Then this will be around 120 degrees, but you notice that the atoms are bent in nature, so this will be bent. And if you look at the actual structure, it looks like that. And notice how we didn't have to do any wedges since this is not a 3D shape, it's flat on a plane. Now let's look at O2. O2 is just this, and you might notice, oh no, this is not on the chart, but that's fine because look, it's linear. So that's your answer, and this is all there is for this video. I wanted to talk fast at the end because I wanted this to be under 30 minutes. And yeah, that's all for this video. Thanks for watching.